last speaker of this afternoon is Andrei Malyutin from St. Petersburg Mathematical Institute. He's going to talk on the number of non-hyperbolic knots.
Thank you very much. I'd like to thank the organizers. It's a pleasure to be talking in St. Petersburg because I'm living here. It's very convenient for me. And as I talk about the number of hyperbolic and not hyperbolic knots. So let's consider the following conjecture. If we denote by Pn the number of prime nodes with the most n crossings, this is the number of crossings in minimal diagonal. And let Hn be the number of hyperbolic nodes with the most n crossings. Conjecture says that this proportion goes to 1 when n goes to infinity. There are several facts supporting this conjecture. The first one is table of small nodes up to 16 crossing. We know that the number of prime nodes is something like that, and the number of hyperbolic nodes between them, sometimes the number of hyperbolic nodes is equal to the number of prime nodes with this number of intersection. And amongst the first 1 million and nodes, we have only about 30 non-hyperbolic. So when you see this table, this conjecture seems very plausible. The second fact that supports this conjecture is that if we randomly generate some knot, usually it will be hyperbolic. The standard system of generation, for example, is with help of break groups. Take some number and consider the braid group with R strings. And you can generate a random braid. For example, you can choose some generators and consider some probability on the set of generators, and then for some time, say t times, add new generators, choosing each next one according to this initial probability you have. And then you obtain some braid, say t crossings, and you can close it to have a knot or maybe a link. And it is a theorem that if t tends to infinity, then the probability that the resulting link will be hyperbolic. Hyperbolic tends to infinity.
To what?
To 1. Yes.
Not everything goes to infinity.
But maybe sometimes.
Yeah, but still, I think that this conjecture is not true. And I tried to write a paper about it several times, but each time I'm always finishing the paper, I found another proof which is shorter and more powerful. So I have no paper, but I have no several theorems about why this conjecture is not true.
Which conjecture?
This conjecture that the number portion of hyperbolic nodes goes to 1. So this is true, and this is true theory. But this conjecture is not true.
You conjecture that it's
Yes. I think that this conjecture that the number of hyperbolic nodes, when you count them in this way, I think this conjecture is not true. So, first of all, because there are another very plausible conjectures which contradict to this one. For example, we have crossing number is additive under connected sum. So this conjecture says that if you have two nodes, K1, K2, for any two nodes, crossing number of the connected sum is the sum of crossing numbers of the complements.
You mean for prime nodes, right?
Yeah, this conjecture is conjecture for any nodes, but we can consider it only for prime. So we have prime. The same thing, but K2 is prime. So this one is stronger, but this conjecture contradicts this one, and this conjecture contradicts this one too. So this one is weaker. Then A prime prime. So this one is even more weaker. And I have another one, even more weaker, which I will talk about today, is prime, prime, prime. So I think many people think that this one may be not true, but this surely should be true. And of course I think this is of course true. So I'm going to prove now that this one contradicts this one. That's why I think that this is not true. At least one of conjecture 1 and conjecture A prime 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 is false.
Can you remind about 2? If t goes to infinity, then what?
Then the probability to obtain a hyperbolic link after this procedure goes to 1, not infinity. I need some number of this. 2. Proof of theorem 2. To prove it, I need some definitions. I'm going to define something, let it be figure 8 notes over some other notes. Then we have some note. Suppose we form some diagram for it. And suppose in some place of our diagram we have two parallel strings. Let it be co-oriented. Or maybe like that. We don't need an orientation, but if we take one, then we do it like that or like that. And then I take such a move on this diagram. The rest is the same. And in this place, I would like to have a double figure 8 note. So I think it's something like this, yes? So, if this is the diagram of a node K, and this one is K1, I say that K1 is a figure 8 node over K.
Is it well defined?
No, there are a lot of figure 8 nodes over K. So I can take another part of diagram, and of course I can obtain some other node. So let 8 of K be the set of all figure 8 nodes over given K. So for each K I have some set of nodes. I think it's infinite, because I can take something terrible here with diagram of my node and then pull out two parallel strings and take this in. And now I have a dilemma. First, that is each
Sorry,
yeah?
one more question. Do you fix the plane diagram or not? Or you consider all possible plane?
All possible. So I said, suppose we have some key and any diagram. If I can take any part of this form, transform it like that, and obtain a diagram of a node K1, then I say that such K1 is 8 node over K. So a lot of K1.
Is it then a finite set or is it a finite set or?
I think it's infinite, but maybe for some. Yeah, I think it's infinite. Maybe for trivial not. It's finite. I don't know. It's not important for our lamp. The first thing that each 8 node over any key is a satellite node. Clearly, it's elegant because obvious, because here we can imagine the torus here noted as side as figure 8 node. So each gamma 8 node is a satellite of the figure 8 node. Because we have this orientation, so the blinding number is 2. So this is obvious, and second, it's not obvious but easy that if K1 and two are distinct hyperbolic knots. Then the set of figure 8 knots over K1 it doesn't is disjoint with the set of figure 8 knots over K2. It's quite easy because suppose we have some knot from here and simultaneously line here. So we should have some incompressible node one for the structure y it is figure 8 knot over K1, and the second torus incompressible y. This guy is a figure 8 not in this sense over K2. Yeah? So this is line K. Somewhere I have incompressible torus knotted like figure 8 knot over K1, and somewhere maybe intersecting with this one I have the second copy of torus noted as a figure 8 knot because I notice here. So it's easy to show that such two tori should, after some isomorphism, be disjoint. And then, if they are disjoint, it can be that one line, like inside other, they are either parallel or completely disjoint and can be set in two different balls. It's standard language. So if they are isotopic, these two torus, then I will obtain that K1 is the same as K2. If they are disjoint, these two tori, then after making this operation backwards, I see that if this one is for K1 and these two is for K2, I see that I perform this operation back. So I untangle this figure 8 knot tangle part and obtain the K1, and in this K1 I see an incompressible torus. This is impossible because the assumption that both these guys hyperbolic. So we have two. And now three. If K is prime, irrational. Irrational means that a great number is greater than 2. If I have some prime irrational knot, then in the set of here 8 knots over this 3, there exists some knot of L such that L is first prime and second closing number of this is my lemma about G8 nodes. I proved first and second, then I will prove this one, and I claim that this lemma implies this theorem, because we know that the number of prime nodes grows exponentially when n is drawn. And we know that this is that one is less than some. For n large enough, we have something like that. So when I prove this, I see that for suppose this is true and this is true, then I can, for all hyperbolic nodes, generate some figure 8 nodes over these hyperbolic nodes, and they will be satellite and prime satellite is, and with small number of intersections. So they should form some part of these primes. And then that goes to 1. So all that we need now is to prove this free. There have some.
Excuse me.
Yeah.
And do you use conjecture A3 primes and this reason?
Of course. So these 3 I can prove only if I conjecture these. So now we're proving this 3. We have some irrational prime, and take some minimal diagram of this. Any minimal diagram. Then the first assertion that, and let's define some notion like an arc. An arc of my diagram is just an arc between 2 intersection points. So for example, when we have 3 crossings, we have 1, 2, 3, 6 arcs. And on the set of arcs, we have 2 natural metrics. The first one is from the inverse image of this circle. So on these arcs, we have a natural metric, and this distance is 1, this distance is 2, this distance between these 2 is 3, is a natural metric here. And here we have natural metric because we have a notion of neighbor arcs. These 2 are neighbors because we can come from one to another without intersecting other parts of the diagram. So this notion of neighbor things is another metric. So, and assertion that I need that let this metric be, say, here. Assertion on any diagram of a node here we have a minimal diagram, but it doesn't matter in any diagram of a node. We have two neighboring arcs such that so we have a diagram with n crossings, and assertion is that on this diagram we can find the two neighboring arcs such that the distance here between these two arcs would be at least 1/3 of the. So we have two arcs, so the path, if we go along the diagram, is long between these two arcs. The proof is a little bit tricky. We need to follow a lemma. Suppose that A, B, and C are three closed, connected subsets of some simply connected space. Connected space X. And suppose that pairwise intersections are non-empty. And then the intersection of all three is non-empty. So it's quite simple combinatorial lemma, but maybe not very obvious. So if we have some simply connected space, for example, the plane or a sphere, and if we have a covering made of three connected closed subsets, and we know that all three pairwise intersecting, then there is a common point. Now, if I have from this lemma, I can prove this assertion. Let's, in each part of the diagram, if I choose, let me split this inverse image in three parts. So this will be A, B, and C. I take these parts, maybe the number of arcs is not divided by 3, but I will choose something similar to 1/3. And then, on this diagram, I have three parts. This one is A, then the second is B, and then C. And then I can color all the plane in each area like this, in each part of the diagram. If this I have A, say B, 8, some colors. Here, I just pick some point and color this in B, and this in B, this in A, and so on. And then I see that I will color all the plane, and it will be 3 colors, and each of them will be connected, and I have pairwise intersection. So applying this lemma, I will, after some technical things, obtain this assertion. And now the next step. From this assertion, I will get this. So I have irrational prime knot. Then I take any minimal diagram. On this minimal diagram, I can choose 2 neighboring arcs, these 2, such that they are distant enough when I go along the diagram. And now I should make my figure 8 knot here. So if these are co-oriented just like this, and if they not co-oriented, I can add this thing, make these 2 co-oriented, and tie my figure 8 knot here. So the result will be figure 8 knot over here. The number of intersection in this diagram will be at most the initial number of intersections plus, if they were oriented, it will be plus 16, and if they not, it will be plus 17. And this new knot will be prime. And this is the key point why this strange thing is prime. That's because when I have a minimal diagram of a knot and choose any such disk intersecting this diagram in 2 arcs, the rest of the diagram, this one, if I imagine that this is on the sphere, so this is the complement of this disk, is a disk with a diagram. So it's a diagram of a tangle. And this complementary tangle, if this conjecture is true, this complementary tangle should be prime. So we have this prime tangle, and inside we have a diagram of a doubled figure 8 tangle. It's also prime. And we have a theorem of Licorice that if you have 2 prime tangles, then the sum is prime. So this guy is prime. That's all. I have some time, but I think that it's last talk, so I can finish here. Maybe somebody.
Let us send the speaker.
There's enough time for questions.
Why do you need to orient them coherently when you make this figure?
Because I'm obtaining figure 8 knots over something, it's the definition.
But
here for this, for here I to prove point 3, I don't need co-orientation, but I need co-orientation to see all of the lemma tree. So here I'm considering only figure 8 node. Because if it's not co-oriented, maybe it's not a satellite. If it's not co-oriented, maybe it's a class like this.
But then the diagram is not
Yeah.
But then the diagram is not Then the diagram is not visible.
Why? Maybe it's minimal, and we have something there.
Okay.
Excuse me, maybe I got lost. What did you use that is irrational?
When I consider this diagram in the complement, so it's, in fact, in general case, it's either, by this conjecture, it would be either prime or trivial. So I need to discard the case of trivial. And if I have here this tangle and here some trivial tangle, then all the knot will be rational. So I discard this case.
It's just program notation. Irrational means not rational, but for example, figure 8 is rational. No, but it's not two braid string.
Yeah.
So
This is the only place we are using irrational.
No, but just for
Bridge number or bridge number?
Bridge number.
Bridge number.
Bridge number.
Because you said trace number.
Oh, maybe it's mistake.
You
Bridge
mean
number.
bridge number.
Can you repeat once more where you used conjecture A prime?
So I used when I, in fact, I used some weak conjecture. So, conjecture A prime. If D is a minimal diagram of a prime irrational, not irrational, non-rational. Non-rational knot, then whenever in this diagram I will find such a disk intersecting the diagram in two arcs, then the complement will be a prime tangle. So I use this conjecture, and this one follows from this one.
Why it follows?
See, suppose this thing is not prime. What means not prime? Then there is some local knot there. Somewhere there we have a local knot. But if we have a local knot, then we have two strings in this complement. So this local knot, it is at one of these strings. And now I can delete the second string and just close this thing and obtain some non-trivial knot K, I know which, yeah? This knot should be inside initial node, yeah, because it's local node. But initial node is prime. So this one is equal to initial one. But when I delete one of these strings, I obtain some diagram which has a less number of crossings. Yeah? And this diagram with some less number of crossings represent some node which is k and maybe something else. So I see that the number of crossings of initial k and something else is less than number of crossings of k, but it's minimal diagram, so it's impossible. And in this case, it's impossible because I took such a strings that deleting one of them, I delete not some intersection, but at least 1/3 of intersections. That's why it's enough to have this conjecture.
Question, you said, so your conjecture A prime on prime contradicts this conjecture?
Yeah.
So you get a lower or upper bound on what that ratio is?
No. So this only proves that we have some portion. In fact, I think that this goes to 0.
Is that implied by this?
But it's not, it's only thing that this conjecture implies, if it's true, that we not go to 1, that's all. But it gives no any ratio.
So maybe no limit doesn't exist even. Maybe the limit even doesn't exist.
Maybe.
But actually, Andrei, what do you think about the actual state of A prime?
I think that it's true. I think that this one might be true. And I think that here, I think it's true. This implies that it doesn't go to 1. But still I think that this 2 and this is true.
So you prove that the third one is true?
No. No. So now it's just a conjecture. And we just know that this conjecture contradicts to this one, and that's all. So nothing is proved. We prove a theorem that these two conjectures are in contradiction.
Why do you think that the small numbers are so close? You have some idea why for small numbers the small numbers are lying close?
Yeah,
Why?
because then we have a lot of satellite nodes. Just each satellite node has at least, 13 self-intersections. So the growth of satellite nodes we can see only in 20s, something like that. There we have a lot of satellites. It's a conjecture. But it's very plausible conjecture because we can just imagine how it works. So in each hyperbolic node we have a lot of accompanying satellite prime nodes knotting to pairs or triples of strings.
Did you try to use the same for
Well, by measuring not the constant number, but the grid number, using grid diagrams. Because for grid diagrams, the constant number is just additive if you, the grid number is additive if you subtract 2y. It is just additive. So you don't need any conjectures. We know that it's additive. So maybe you will get the proof.
That's right.
You can try, yeah?
But the proof is written only in this blackboard, or there is some preclinic, or?
I have an annotation of
Okay, so there are no more questions, and I think let's thank the speaker, and let's thank all speakers of this afternoon.